Welcome to the presentation of my paper, titled Learning Visual Locomotion with Cross-Modal Supervision. In this work, we study the question of how can a robot get better at what it's doing, which is generally referred to as continual learning. We study this question in the context of vision-based leg locomotion. We have recently seen many works that train a sensory motor policy in simulation to control a legged robot. These approaches are generally exclusively trained in simulation, and the policy is then frozen and applied in the real world without any further learning. For this reason, they generally use a depth map as input to the policy, since depth is very easy to simulate. In this work, we make a small modification to make the problem interesting from a continual learning perspective. We train such a policy to operate only on RGB information. In contrast to depth, it is impossible to get high-quality RGB simulation, which necessarily requires learning in the real world. In addition, some characteristic of the terrain could be totally invisible to a depth image, like changes from grass to sand to water, but still very important for locomotion. But since we can't simulate RGB, how are we going to train such a policy? To solve this problem, we use as intermediate representation some terrain parameters, like for example the terrain geometry and friction. In addition, we provide to the action policy proprioception, which is the knowledge of the robot feet and leg position. We can now train this action network, here represented in blue, in simulation. Many papers have shown how to do this, so I'm gonna skip the details. But the real question comes here. How can we train an estimator of the terrain parameters from a single RGB image? The problem is that we cannot use existing dataset or pre-trained networks. Indeed, there are not such networks that capture all parameters that we need. In addition, we can't collect a new dataset ourselves and ask humans to annotate it, because some of the properties we need, like for example friction, are very difficult to annotate. So, what can we do? Well, proprioception, which again is the knowledge of the position of the robot legs and feet, is very informative of the terrain parameters. If I measure where my feet are, I know that the terrain below me is uneven. However, proprioception can only estimate terrain parameters below the robot, while we want vision to estimate these same parameters, but in front of the robot. To train it to do so, we take the estimate from proprioception, that here you see in a one-dimensional representation, and we shift them with time. We can now use this time-shifted proprioception as a ground truth for vision. Essentially, we train vision to predict future proprioception, and we can run this procedure only with data collected in the real world. At the very beginning, our terrain estimator is completely untrained. Therefore, the policy will essentially be blind and resort to use its legs as blind people use their sticks. But still, it will be able to collect data to bootstrap the estimator. Indeed, the next time the robot is there, it will use vision to predict the discontinuity in advance and run up the stairs. And while doing this, it will collect even more data. And what we found is that the more data, the better. Therefore, I took the robot all around campus and trained it on all terrains that I could find. After only 30 minutes of data collected in the Berkeley campus, the robot started to work very well. But now the question is, does this policy work well even outside of the Berkeley campus? To test this, we brought our robot to the Berkeley Rose Garden, which is our park with complex and discontinuous terrain, like you see here. Surprisingly, the policy generalizes to these complex terrains, like for example the construction zone in here, where at times, due to the fact that the terrain is slippery, some precise foot placement is required to not fall. And the fact that the policy continually learns from its own experience makes it very adaptive to disturbances. To test this, I'm now going to change the visual field of the robot by rotating its camera of approximately 30 degrees. Note that this change is completely unknown to the algorithm. Well, as we expected, the robot struggles to go up. However, while struggling, it still collects data. And fine-tuning the estimator on just 1 minute of data collected in this distorted camera setup, the robot is back to its original performance. So let us zoom out and see what we learned from this project. First, effective locomotion needs to go beyond depth. RGB contains so much more information. Second, since RGB is hard to simulate, we need to rely even more on continual learning in the real world. And using the coupling between different sensors is a very effective way for doing this. Third, we have seen that continual learning in the real world enables adaptation with very little data, which neuroscientists usually call plasticity. And with this I'll conclude, and I'll thank you for your attention.